So hello, everyone, and welcome to the third webinar of this weekly series. So my name is Declan Bennett. I'm the training coordinator for the Centre for Research Training in Genomics Data Science, which is funded by Science Foundation Ireland. So I'll just give you some kind of background into our involvement with this webinar series. So the CRT is a cohort-based PhD training program, which is funded by SFI. We have over 150 science group leaders or PIs across 7 Irish universities, and we aim to train over 100 PhD students in genomics data science over 4 intake periods. So in the first 3 months of a student's PhD, we run a residential training program. So this is where all the students attend the University of Galway and undertake training in the fundamentals of genomics data science and its advanced applications to human health. They then go on to enroll in the university of choice across the University of Ireland to complete their PhD projects. So this webinar serves as kind of a keynote address in a part of a week-long set of masterclasses where trainers associated with the African Society of Human Genetics will be delivering in-person training on the applications of genomics in human health across the African continent. So I think Vicky is going to talk about some upcoming meetings, and then we can get started with the webinar.
Thank you very much, Declan. Yes, we just wanted to highlight, if you can move to the next slide, we wanted to highlight 2 upcoming meetings that are supported by the African Society of Human Genetics. This is the organization that is co-hosting these webinars. So the first meeting is happening in December in Morocco. You can see that on the screen. It's actually going to be a very exciting meeting. And it's happening December 12th to the 17th. Registration is still open, so anyone keen to attend, please apply as soon as possible. The second one is a much bigger meeting. Please go to the next slide. Which is the International Congress of Human Genetics. This is scheduled to happen in 2023, February. Check out the website, and if you have any questions, do let us know. This is being co-hosted by the African Society of Human Genetics and by the Southern African Society of Human Genetics. This happens every 5 years, and because of COVID, we've pushed it out to allow in-person attendance. Thank you. We look forward to welcoming you in Cape Town. I'll hand over to Declan to introduce our first speaker, our speaker for the day. Thank you.
Okay, thanks, Vicky. So today we have a fantastic talk again lined up by Dr. Segun Fatumo. So Dr. Fatumo is a computational geneticist, associate professor of genetic epidemiology and bioinformatics at the London School of Hygiene and Tropical Medicine, fellow of the Advanced HE, and a Wellcome International Fellow. He leads the African Computational Genomics Research Group at the MRC, UVRI, and LSHTM. His group's expertise includes, but not limited to, genome-wide association studies, polygenic risk scoring, fine mapping, Mendelian randomization studies, and drug targets discovery. He was recently awarded a prestigious Wellcome International Intermediate Fellowship to lead an innovative research program at the MRC, UVRI, and LSHTM. Dr. Fatumo co-leads the Nigerian Non-Communicable Diseases Genetic Heritage Study Consortium and co-directs the Nigerian Cardiometabolomic Genomic Study, NICGEN. A concerted effort to see over 100,000 Nigerian participants in the eponymous study, which will seek to understand the genetic basis of the highly prevalent non-communicable diseases in Nigeria, such as chronic kidney disease, obesity, amongst others. So with that, I'll hand over to Dr. Fatumo.
So thank you very much for the kind introduction. I'm going to share my slide and start my presentation. So good morning, everybody. Good afternoon, good evening, depending on where you're joining from. Once again, I would like to say thank you to the organizers for inviting me to make this presentation. So today, my presentation is titled Complex Disease Gene Mapping and risk profiling for African population. My name is Segun Fatumo. I'm an associate professor at the Department of Non-Communicable Disease Epidemiology at the London School of Hygiene Medicine in the UK. I also lead a group called the African Computational Genomic Group at the MRC, UVRI in Uganda. If you have any question that I'm not able to answer now, please feel free to send me an email on this email, segun.fatumo@lshgm.ac.uk. If you would like to tweet any of the comments I make today, please feel free to tag me on sfatumo on Twitter. So I always like to start with this slide because most of the time we have a mixed audience. And I like to say that to give some statistics about Africa. Actually, Africa has about 1.4 billion inhabitants living in there. So Africa is the world's second largest and the second most populous continent in the world. Like some people may not know, Africa is not a country. Africa is a continent with 54 different countries, speaking more than 2,000 different languages with more than 3,000 different ethnic groups. So currently, more than 50% of African population, they are children. So the average age of people in Africa is probably about 18 years old. In Uganda, where I do most of my study, average age is about 17 years old. So by 2015, 40% of the world children will be living in Africa. So these are very important for what I'll be speaking about today in terms of genomics, genomic medicine, and broadly, precision medicine. So why is African genomics very important? Why do we care about African genomics? There have been several studies, multiple studies that have confirmed what is called the Art of African theory. So meaning that all of us, all women come from Africa. So as we know, African population have more genetic diversity than any other population in the world. And this genetic diversity is very key for our heads. And that was about 100,000 years ago. So when they left Africa, so they carry with them only a small proportion of African genetic variation with them. If you look here on the left, top left here, you see here where I show the map of Africa. And what you see here is a lot of genetic diversity within African population. So if you look at the rest of the world, you will see that what you see in the rest of the world is more or less like a subset of what you have in African population. So what that means is that there are more genetic diversity in Africa, and African genomics have to be studied. So also very important that I should mention is that there is even larger genetic differences between or within African than between African and European population. For example, if you look at this plot again and look here and look at this side, you will see that there are more diversity if you look at South Africa compared to either East Africa or compared to West Africa than comparing Africa with European population. So there are larger genetic diversity even within Africa than between African and European population or between African and Asian population. So all this diversity, they have implication. So genetic study of African population are crucial to fully understand the modern human evolution and also the effect that it has on disease. So secondly, this finding implies that research from genetic study in non-African population, including their clinical relevance, may not be generalized or generalizable to African population. So if we continue to study non-European population, so the finding from those non-European population may not be generalizable to African population. So thirdly, so this also implies that there are many genetic variants yet to be discovered yet. If you are aware, a few weeks ago, which I will show later in my presentation, you see a study which is genomic study of height in diverse population. And the paper reported that all the loci that are shared with height has been discovered. But the truth is that there might be some other loci that have not been discovered because African population have not been studied. So this findings implies that result from genetic study in one subpopulation, in African population, may not also be transferable to another population in Africa. So there have been repeated calls and warning that genomics in Africa must be studied. And here on the left here, so I show the number of genomic study in percentage that have been studied in 2016. In 2016, 81% of all genomic studies that have been done were done in individuals of European ascent, only 3% in Africa. 3 years down the line, in 2019, we see that African reduced from 3% to 2.03%. And another 3 years down the line, recently, in the paper that we published recently in Nature Medicine, we reported that only 1.1% of African genomics has been studied. So we see that we're not doing very well. So there is a decline in number of genomics that have been studied in African population. So very interesting to know is that even the 1.1% African in genomic study are mainly African Americans or Black participants in European population. So I'd like to make this warning that if we continue to study a small number of African in diaspora, that is the African American Black participant in the UK and Europe, and we group them together, call them, we put them together as a broad category for African ancestry. So what will happen is that we'll continue to promote genomic imbalance, we continue to widen age disparity, and fail to capture the genetic diversity in Africa. So again, we must think and we must look to study genomics of individuals in continental Africa. Here I show an example of one of the well-characterized biobank in the world. It is called UK Biobank. So UK Biobank currently have about 500,000 people. And that also includes about 38,000 individuals with non-European ancestry. So here you will expect that even in this cohort that have non-European ancestry, scientists will be interested in studying the non-European ancestry. But what we found out is that 93% of all study still excluded this small 38,000 individuals that are non-European. So again, our colleagues like to talk a lot about the need for diversity, but when the opportunity is shown forth to analyze data from non-European, they exclude them. So we must walk the talk. So here, again, is showing one of the biggest consortium trying to aggregate a biobank all over the world. You see here, more than 2.2 million individuals are being put together for biobank. So you see from all over the world. So if you look inward and look at the African map here, you see that there is no even one biobank from African being represented. So what we see is that scientists tend to utilize data sets that are well curated and easy to access all over the world. And again, excluding the African biobank. So here, this is the paper I mentioned previously. This was a very an excellent paper that was published in Nature. And here it was a GWAS, including 5.4 million people all over the world. So what they did was to aggregate more than 280 GWAS. And you will see, if you read the paper, even though they mentioned that there's one study from Africa, but you see that even that one study from Africa is actually a part of an African-American study. So more or less, none of the study here is from continental Africa. So this paper have more than 600 authors, none from continental Africa. So they claim to have found all association. What I want to emphasize here is that in the last 10 years, thanks to AfSHG Africa and other initiatives from Africa, there have been some GWAS of height in continental Africa. So it's not that the GWAS from continental Africa is lacking. So my question is, why exclude continental Africa from such study? So in order to improve representation of African in genomic study, we must engage, we must recruit participants from indigenous population, we must also analyze them. So what we are doing is that I'm currently leading some African genomic program in Africa. So one of them is called the Ugandan Genome Resource. Uganda Genome Resource has about 5,000 participants that were genotyped on a 2.5 million Illumina array, additional 2,000 on that were whole genome sequence from a cohort, a community of about 22,000 inhabitants. So there's a plan to expand this study to include proteomics, metabolomics, epigenomics, and single-cell genomics. I'm also currently now leading what we call the Malawi Genome Resource, which we are generating from a Meru cohort that is led by Professor Mia Crampin in Malawi. So this cohort has about 25,000 people from a rural and urban community. So we are currently genotyping about 7,000 individuals on H3 Africa array, and we plan also to expand this. And so thirdly, I'm co-leading a new consortium that was founded in Nigeria about 2 years ago. So it is called the NCDGHS Consortium. And we are working on what we call the Nigeria 100K Genome Project. So this is a private-public partnership project. There are multiple centers across Nigeria in different states of Nigeria. We currently have 2 projects. One of them is based in the community. One is based in the hospital. We have recruited over 100,000 individuals in the last 2 years. We are doing whole genome sequencing, genotyping, whole exome sequencing, and there's a plan to expand this across Africa. So I'm going to start with the Ugandan Genome Project, which I described previously. So we have this cohort that was established in 1989. Like I mentioned, it's about 22,000 people in 25 villages in a place called Shamulibua in the sub-region close to Etebe. So we have an established community advisory board who consists of stakeholders, people in the community, not scientists. They are mainly normal people, leaders in the community, such as pastor, imam, cultural leaders who are involved in the direction of our study. So every year, so we survey, we do different medical survey, including now doing some genomic epidemiology study. So since 2011. So we leverage local resources at our organization in Uganda. I've mentioned the GPC, which is the cohort where we contact people, where we administer questionnaire and collect sample. We leverage a biobank in our organization and store the sample that we collect from the GPC. We have facility where the sample can be tested for different phenotypes, including kidney and all kinds of non-communicable disease and communicable disease. So we have what we call the Uganda Medical Informatics Center, which is more or less like a high-performing computing, where all data that are generated are being stored and analyzed. So we are also collaborating regionally in Africa, collaborating with other studies in Africa, including ADAM, DDS, and DDC, to boost the number of samples that we have. And here, just showing the different phenotypes that have been analyzed. So in order to demonstrate the value of African genome, in 2019, we published our work in Cell. At that time, this project represents one of the largest collection of genome-wide registration study GWAS and whole genome sequencing in Africa. Like I said, this study show data that were genotyped on 2.5 million array. And we also incorporated data from other parts of Africa, including data from Nigeria, Kenya, South Africa, making a total of 14,000 individuals across Africa. And here, just to show the data from Uganda, you see a lot of diversity from just one local community in Uganda. You see different ethnic groups represented on this PCA. So we see an evidence of a population substructure which cause confounding, and there has to be an appropriate model used for this kind of analysis. So as you may expect, we find a higher level of genetic diversity in Uganda population that is not seen in similar study in European population. We find around a quarter of genetic variation identified in Uganda population have not been discovered before. So specifically, you see we had 9.5 million novel variants that are not represented in either 1,000 genome projects, phase 3, African genome variation projects, and UK 10K reference panel. So we also demonstrate the value of African genome resource by creating the African unique reference panel using the data set I mentioned previously, that's 2,000 whole genome sequence, and also the African genome variation project, and additionally 1,000 genome project. So what we see is that the unique reference panel that we created performs existing imputation reference panel, particularly when imputation is done into East and South African population. So this slide showed a list of novel genetic associations that we found to be associated with various cardiometabolic traits and disease. It also showed a list of distinct associations at already known loci. So as you may have noticed on the last column and the second to last column show the minor allele frequency in African population, and the last one showed the minor allele frequency in European population. What you will see, notably, you see allele frequency of 0. So meaning that these variants are monomorphic in European population, maybe simply mean that they are absent in European population. So again, that explains the reason why we find this association in African population, because they are not present in the European population. And that could justify the reason why I said the GWAS of height in 5.4 million people globally may not actually have discovered all the genetic variants that are shared with height. So our study also leveraged on lower linkage disequilibrium in African data sets. Our fine mapping analysis resulted into narrow, credible interval for most of the traits. We can see that we're able to map 16 out of 41 distinct loci into a single SNP in the credible set. We're also able to resolve previously identified association with HB1C. So very interestingly, the Uganda Genome Resource also offers us opportunities to study the extent to which genetic differences encode differences in traits and disease. So here, this study is showing the assessment of heritability that we did in all the 34 cardiometabolic traits using mixed model that also model the environmental correlation. So what we found that the height is less genetically determined in Uganda relative to what you will see in European study. You can see that the narrow sense heritability for height was 49% in Uganda compared to about 80% in the European population. One reason for this might be environmental factor such as maybe nutrients in Uganda population. And in contrast to that, so we found that the heritability estimates for LDL, lower cholesterol, was significantly higher in Uganda population, about 54%, compared to 20% in European population. And on a whole, so this finding highlights the usefulness of examining genetically diverse population within Africa like ours. Here, I'm showing an example of what we do before we start our sample collection and what we do also even after sample collection, how we engage the participant. So here is just an example of our community support for the research participants. We don't just go there, collect sample, do analysis and go away. So we also engage the participants and also give do different kind of activity, including just one of them that we did recently this year, January this year. Here also an example of getting to know the participants and support them. Here is also one example. Here is another example, and another example, and many examples showing how we engage and support our participants. So collectively, so our findings from a small data set show a great potential and value of African genome data for genetic discovery. So from what I've said so far, what we have learned from the Uganda cohort is that community engagement, and this is not the same as doing consultation, and it's not the same as doing research announcement, telling people that they want to do study. So community engagement is key for genomic study, especially in indigenous population. We think that it is not just right to show up when we need to collect sample. People must be engaged and must be supported. So we also learned from the Uganda court that it is not ethically or morally right. And this is me in Shamulibwa, in that community where we go to collect our sample. So it is not right, it is not ethically right or morally right to think about our research participants as data or number. We must think about them as an integral part of the solution that we aim for. So here is an example also of an informed consent. And in one study that we're doing, I'll just go to this part where we're trying to do a genomic study. And in Africa, many parts of Africa, so the word genomics, DNA, genetics, they are not literally translated to local language. There's no direct word to translate them. It's always very difficult. And if you must get an informed consent, we must be clear that this must be a process that is actually informed, that the participants actually understand what we are trying to do before they sign a form. It should not just be a form sign activity, it must be truly an informed consent. So in this study, we have the scientists trying to get across to the participants who don't speak English, and we need to translate genetics to the local language. So what we found is that when we did the translation to local language, we also attempted to translate back what we translated. So when we translate back what we translated, so genetics translated to mean generational causes. So what this means is that we must do validation of any translation to local language and be sure that people actually understand what we are trying to pass across to them. So in that population, which is on the average of about the average age of about 30 years old, we found a relatively high prevalence of risk factor for CVD in that population. Unfortunately, there's a low level of awareness about the risk factor that they have. This is very important because in Africa, many people live in the rural community, and our population is a true representation of many people in Africa. For example, we found that none of those with high cholesterol was aware. In one pilot study that we did, 80% of those with hypertension were not aware. We have facility, we have a clinic in Shamulibwa in the community where people can be supported and be treated. 57% of people with HbA1c that is abnormal were not even aware, but we treated them. And here we have to provide the feedback before you can treat people. Of course, particularly we have to provide feedback to every participant that are giving consent to get feedback for their study. Here just to show that Uganda, there's a clinic I mentioned previously where we see an average of 60 to 80% and support them for various outcomes that we see from the sample collected. So what we have learned from this population is the need to integrate feedback to the genomic study. We must remember that research participants may not have the capacity to understand your complicated journal in nature or in science. So we must find a way to communicate back to them what we study. So we have now extended our study, collaborating with MVP, that's a Million Veteran Program, which has about 57,000 African ancestry individuals, and also including 7,000 Black participants from UK Biobank. So in one study where we are looking at univariate and multivariate GWAS discovery of blood pressure in African ancestry individual. So what we do here is that we aggregate some data from the MVP, which I mentioned previously, UK Biobank, and our regional collaboration in Africa to see whether we will find loci that have not been found before. So we are applying both univariate and multivariate approach in this particular study. So what we found is that both univariate GWAS and multivariate GWAS find common gene, common loci, but they also individually are able to find loci that are not found by one approach. So again, leveraging on the data that we have, so we are using this data to derive body shape using principal component analysis. using data from the anthropometric that we have collected from Uganda and also from South African cohort. So what we did is that we defined what body shape is using PCA, and we perform GWAS for body shape in 6,400 people in Uganda and 2,500 people in South Africa. Here we found some novel loci that are shifted with the newly derived body shape. So this work is currently now under review. So this paper is currently now accepted and published. So here we use the same approach, the same PCA approach to define what is called metabolic traits, metabolic syndrome, or a cluster of cardiometabolic risk factor. Here you can see we have HbA1c, WC, blood pressure, and HDL, trying to see the clustering around them, metabolic syndrome, and defining that as just one phenotype. So again, we find some association that were not found previously if we look at each of these phenotypes individually. So what we found is that leveraging the correlation and relationship between those phenotypes, we're able to identify new loci that were not found previously. So here we assess whether lipid traits and have any causal effects on type 2 diabetes in African ancestry individuals. Also including assessing whether drug inhibition that had been known before for type 2 diabetes also is applicable in African population. So what we found here is that using Mendelian randomization approaches, so we show that higher genetically appropriate type 2 diabetes, LDL, total cholesterol, and HDL, they were associated with risk of stroke in African ancestry. And there was no evidence of difference in this estimate between African and European population. So this analysis again supports a causal effect for type 2 diabetes, lipid traits on stroke in African population, and we don't see any difference between African and European population. In some other study, we see different, but this particular study, there's no difference between African and European population. So like you're aware that up to 60% of type 2 diabetes in Africa are currently undiagnosed. And here, so what we do is to predict, derive polygenic risk score and see if they transfer into African population. So on the left here, we are using very large data set from different populations. So one of them is type 2 diabetes GWAS in multi-ancestry population, which has more than 1.4 million individuals. So the second one is type 2 diabetes GWAS from African ancestry, African American population, which has only 50,000 individuals. And the last one is European population with 1.1 million individuals. So what we did was to derive PRS from these different data and test their transferability into South African population with 2,500 and validate that in another population. So this table shows the number of type 2 diabetes cases and control in the base discovery data sets. So those three large data sets I mentioned. So the multi-ancestry, for example, has more than 200,000 cases of type 2 diabetes. The European ones has more than 150,000 and African American only 24,000. So the target discovery I mentioned, South Africa, about 1,600 cases and 981 control. So what is very important on this slide is that the best predictive PRS from these three base data sets, they were all significant in South African population, like you can see from here. So, but we observed that the highest variance of 1.1% as indicated by R square, which is what I'm pointing to here, and p-value of 3.9 times 10 to the minus 9 was seen in African American derived PRS. So we showed that the African American derived PRS, even with lower number of sample, is transferring much more to African population. So again, for validation, So we noted that all the best PRS were all significant into the validation, which is a data that has people from different countries in Kenya, in South Africa, Ghana, West Africa, and also Nigeria, West Africa. So what this means is that the African American PRS has the highest predictability as indicated by R-square of 2.92 in that Adam population, and p-value of 9.38 times 10 to the minus 24 in the combined Kenya, Ghana, and Nigerian dataset. So we also decided to evaluate the transferability of PRS in different individual African countries. Here you see Nigeria, Ghana, Kenya, and Kenya. So the bar shows the transferability of African-American derived PRS in green and the multi-ancestry PRS in yellow. You see different countries like I mentioned. So as I've noticed here, so the African-American derived PRS is transferable or predictive in all the country compared to the multi-ancestry that was less predictive in East African Kenya population, like you can see from here. So this might be due to the fact that the African-American derived PRS more people probably from the West Africa, including Nigeria and Kenya, and you can see that the multi-ancestry is not transferring much more as expected. So again, we showed that the model with the conventional risk factor of age, BMI, and as well as 5 PCA and sex had an area under the curve, which is AUC of 67.9%. Why that's one of the African-American PRS, and including the 5 PCAs, age, and BMI and sex, at 69.8%, which is higher. So this shows an improved discriminatory ability by 1.9% with the addition of the African-American PRS, if you compare that to the conventional risk factor. So what this means is that we show that the African-American derived PRS is best predictor for type 2 diabetes in continental Africa compared to the European and the multi-ancestry PRS. So this work was published this year in Diabetes Care. If you're interested, you can have a look of the state of the analysis that was done in this work. So we now use a very similar approach for another phenotype, which is lipid traits. Again, compare different PRS derived from multi-ancestry, African-American, and also the European into continental Africa. So again, what we found is that the African-American derived PRS is transferring better generally than the multi-ancestry or European population. And this was done into the South African population. So we were very excited about our prediction into South African population. We now decided to evaluate whether using the same discovery data set would lead to similar prediction in the Uganda population. So unfortunately, our PRS prediction vary greatly between South African Zulu population, which was showing like a square of 8.14% for LDA in South Africa, but now showing 0.026% for Uganda. So what this is telling us is the difference between two different African population, and there might be many factors that contribute to that. So this paper again have been published in Nature Medicine, and detail of that can be found in this paper. So collectively, our PRS work show a need for improved representation of African in genomic study and ensuring that generalization of findings for precision medicine. So if you are aware that many countries all over the world are now establishing their genomic medicine. I've mentioned UK Biobank with a program that has 500,000 individuals. All of us project that has a program in the US with 1 million people, Australia, Brazil, China, Denmark, Switzerland, Estonia, Finland, because of the importance of this. What you will notice is that in Africa here, so there are no really any genomic initiative for any country in African population. And even people are very, very specific for precision medicine, such as for type 2 diabetes. You see different initiatives coming all over the world. Again, Africa is just lacking in this kind of initiative. So like I mentioned previously, our aim is to improve representation. I've talked a lot about the Uganda Genome Resource, and so now the NCD GHS Consortium, which is working on the Nigeria 100 Genome Project, is also a very exciting study that we are currently doing. So in order to improve representation of African genomic study, 2 years ago, so we started creating what is called the Nigerian 100K Genome Project. So this is a partnership, a private-public partnership project with a biotech company in Nigeria and in the US called 54Gene, led by Dr. Abasi Eni Obon. And here you see a partnership with Professor Salako here, who is Director General of Nigeria Medical Research in Nigeria, and Professor Oyekomi Nash, who is also a director in the Nigerian National Biotechnology Agency. And here is a colleague in academic trying to put expertise together to lead in forming scientific objective for this study. So so African scientists must stop waiting for government's money that will never come and think about an alternative. And one of such is a private-public partnership that we form. So we published a paper this year in Nature Genetics, so where we define a 5-point agenda of what we plan to do with NCD-GHS. And so basically, we are collecting sample in 100,000 people and more. We're designing a custom array. So we are designing study for whole genome sequencing, whole exome sequencing, and genotyping. We are also empowering African scientists, including trying to do capacity building and also training people. But the detail about the paper, about what we are doing, AfSHG, like I mentioned, has been published in this paper for details. So in brief, this project is divided into two. So there is the hospital-based project, which is called the Heritage Study, looking into different hospitals and trying to take sample for different diseases. And here is another project which I lead. It's called the Nigerian Cardiometabolic Genomic Study in the community, applying a very similar model that we use in Uganda Genome Resource. So the NIGGEN project basically is trying to estimate prevalence of a range of cardiometabolic traits and produce a comprehensive catalog of human genetics variation in Nigeria, and also what the contribution of those genetic variants might mean for health and disease in the Nigeria population. And like I said, we are looking at different states. Nigeria, looking at the south, the north, and the west, and trying to link that to different teaching hospitals in Nigeria. So lastly, a project that we started working on is the Malawi Genome Project. So this project, like I said, has more than 2,000 adults that were recruited from a rural community and also from the urban community in Malawi. There have been a range of NCD that have been collected, including communicable disease that have been collected and phenotyped. So currently we're genotyping 7,000 individuals on East Africa Illumina array and plan to expand that. So very exciting about this project is that the study design, the sample recruitment, the storage, biobanking, biomarker testing, DNA extraction, and the first large-scale in quotes of human genetic variants is done in Africa. Analysis will be done in Africa, and the perfection will be led in Africa. So this is a very exciting project that is upcoming. So to conclude, so again, this year we published this paper in Nature Medicine, where we provide a roadmap to increase diversity in genomic study. And here is a roadmap that in order to improve diversity in genomic study, there must be willingness from our colleague researchers to analyze data to design study from African population and also other underrepresented population. There must be willingness from the community and the funder to focus on the other underrepresented population. We must leverage on infrastructure that are available. I'll show an example of infrastructure that are available in our community in Uganda, and there are so many other such infrastructure all over Africa. that we must leverage on. There must be some strategic funding. A very good example of such strategic funding was the AfSHG Africa funding, which was focusing mainly on recruiting data from the African population. So capacity building is very key, and we must also participate in the global consortia. So in conclusion, Africa has the greatest genetic diversity, and as such, African genomic data and resources, they are key for genomic and precision medicine. Unfortunately, genomic research, as we know today, has a white net bias, which we must take effort to fix. So for what I've shown today, I've shown that from relatively small-sized African genome resource, including from the Uganda genome resource, we have shown great value of this resource for novel genetic association and also for genetic risk prediction. So the existing data biobank that we have in Africa and the new one that are coming up in Africa will help to fix some of the current genomic imbalance. So I would like to start by appreciating members of my group, the African Computational Genomic Group in Uganda and AfSHG, and also my partner and associate member of the group. I'm particularly need to acknowledge my founder, particularly welcome, which is currently funding my fellowship and all others. Thank you very much for listening.
Thank you so much, Segun. So some questions have come through on the chat. So we have some time to get through some of those. The first is from Matthias. Why was the heritability in LDL much higher in Ugandan than European ancestry?
Yeah, that's a very interesting question. I've asked that question over and over again. So if you don't study the African population, we will not even know in the first instance. So the one, not only LDL, from what I show, I also show height. That's height, heritability for height also is different between Uganda population and the European population. One reason could be nutrients. People live, there are other factors that must be put into consideration, environmental factors, such as what people eat and how they live their life. So that's all I can say about the difference that we see in terms of heritability between those two populations.
That's great, thank you. And what multivariate GWAS methods did you use? I presume this is in the Ugandan study as well.
Did you say what's kind of GWAS?
Multivariate GWAS, so what methodologies or tools did you use?
Yeah, so there are so many tools that we use. So first of all, we must remember that in rural population in Africa, people tend to live together. I mean, people that are relatives or family. So you are going to be seeing a lot of relatives in your study, and this must be accounted for. So we need to apply a mixed model approach to cater for relatedness and also some cryptic relatedness. For multivariate GWAS, we've used MTAG. MTAG has been a very fantastic software. There are also other software we've used. Recently, we used one software called Scopa for the MET-S project I mentioned. There are many software that we also use GEMA because GEMA implemented mixed model.
Thank you. So Ashley has asked, thanks for a great talk. Just a couple of questions, please. One, for the Ugandan resource or any other African cohort, is there any data collected on skin disease such as eczema, which has been shown to be more severe in African ancestry compared to Europeans? And two, if there is a high genetic diversity between African populations, would a meta-analysis have to adapt a random effects model?
Excellent question about the meta-analysis. Okay, so currently we are working on a project that is called Kidney Gen Africa. What we are doing is to aggregate data set from all across Africa, including West Africa, East Africa, South Africa. And as you expect, there's a lot of diversity and differences between this population. So what we are doing first, because we need to test what will be the best way to do meta-analysis in African population. So what we are doing first is to meta-analyze all the study from West Africa. We cluster different study by region. So we look at West Africa, we look at Southern Africa, we look at the Eastern Africa, and we try to assess relatability, assess heterogeneity between those, and we now pull them together. So we don't know a lot about how whether this is going to be like a fixed effect or random effect until when we do this study before we know what is going to, and this is also going to depend on how phenotype were defined in those different populations. So for the first question about about whether we have eczema or skin disease, I have to check. You know, like I mentioned, in Uganda Genome Project, we've looked at this. We've gone back to this population for more than 30 years. For every year, we have studied different kind of phenotype, including currently looking at different mental health, also including looking at depression and all that. So I have to check whether we have anything as to with skin disease. I'm not, it's very, very uncertain, but if we do, maybe just send me an email and I can have a look at it. So what we've done in terms of phenotype that we don't have is that we found collaboration because we're able to contact the participants and introduce to them a new study that might be of interest to them.
Okay, thank you. So given increasing ethnic mix in urban areas in Africa, what is your comment on the extensibility of research in rural areas in Africa where there is no to less ethnic mix to urban population?
So if I understand that question very well, so I think there is a lot of diversity in even rural community. So the Uganda genome result that I show you is just one cohort that has different ethnicity. You know, I showed that one cohort in Shabulibwa having about 10 different ethnicity clearly show from the PCA. So I think the fact that people live in the rural community or urban community may not imply that there are no different ethnicity living in those in either urban or rural community.
Okay, so Elvis has a question on public-private partnerships. Can you share some operational challenges in translating genomic studies to precision medicine in Africa using the 54 gene as a case study?
Okay, so the answer is that I don't know because we are not yet at the stage of translational genomics. So we are still at the elementary stage of this partnership. So what we've done in the last 2 years was mainly to collect sample in 100,000 people in Nigeria. And currently we've done whole genome sequencing in a few of them in different ethnic groups. We are not doing genotype, we're not trying to genotype some of them. I think we are far away currently from the stage of translation genomics. But if you talk about the partnership, so far, last 2 years or thereabout, for me, it's been a very fantastic partnership so far.
Great, thank you. So the next question is more for the society. So if Vicky is here, she can reply to Lily's question. Yeah, so Kevin has a question. Great talk as usual, Dr. Fatumo. Is the unique reference panel you generated from the Ugandan genome resource accessible for imputation?
Yes, the answer is yes. It is available now. When we created that, so it's called the African Genome Resource. So if you go to the Sanga website, the imputation reference panel for Sanga website. So what is called the African Genome Resource is the resource that I'm referring to, which we generated.
Okay, and that's available on the imputation server itself, yeah?
Yes, that's correct.
Fantastic. Okay, so I think if there's no more questions going through, we can end the webinar here. So just thank you once again. That was fantastic talk, and I guess kind of look forward to seeing the science that comes out of these genome projects as they build in size.
I think there's a question about top med panel.
Oh, yes.
Okay. So we have a student, a PhD student trying to compare our reference panel to PubMed, another reference panel, when you are inputting into African population. So what we find is that from SNPs with 900 frequency of maybe 2%, I'm not quite sure now, you have the same level of accuracy with PubMed. But when you look at a SNP with a real SNP, maybe like 0.1% and below, you see that the reference panel from the African Genome Result perform better than PubMed. So that's what I can remember about that. So is the real variant, we have the African reference panel perform better, but for the common variants, we have African reference panel and PubMed perform at the same level.
Awesome. Thank you. Okay. So, Vicky, if you want to just kind of clarify the deadlines for the society meetings, I can finish here and leave Dr. Fatumo go. So thank you once again.